Okay, please. Thank you. So, the aim today is to answer a question by Martin Escado. I think he asked this some time ago, actually. So, are there models of type theory that do not have propositional truncation? And I think people who are less familiar with semantics maybe find it a bit mysterious sometimes. So, like, as another way of asking the same question, is there a clever way to construct propositional truncation from other type constructors and univalents, or is this impossible to do? So that's the question. So the answer is, okay. Well, depending which one of those questions you're asking, the answer is yes or no. So the answer is that there are models of type theory that do not have propositional truncation. So no, there's not a clever way to construct propositional truncation from other type constructors. So first theorem on the slide here is that there are locally Cartesian closed categories with some co-limits. So it's an initial object and disjoint co-products and W types that are not regular. So not regular is the reason for the title. Regular. Okay. Actually, this first construction turns out to be like the easier one, and the kind of slightly more complicated construction is this one, where we have models of intentional and univalent type theory with a cumulative sequence of universes with a bunch of type constructors, probably including the circle type, and and there's a type in the lowest universe that does not have propositional truncation in any universe, where propositional truncation in any universe has a slightly technical definition that I didn't write out, but the point is that there's like different ways to state propositional truncation, and the weakest version is where you kind of restrict the induction down to like one fixed universe, and even this weak version it's not hold in the model in this second. Okay, so in general, we are using kind of realizability called Lifshitz realizability. This is like one of my favorite kinds of realizability, so it's nice to have an excuse to use it. So the way I'm going to talk about it today is originally comes from kind of a paper by Jaap van Osten, and then there's a bunch of variants based on that idea due to Lee and Van Osten, but I don't like how they did that. So there's a kind of later work by Nico Rashan and Lee. So we did this for set theory, and then there's a kind of another variant by Dimitris Kouzoulis, which this is probably closest to the way I'm going to present it today. The way we present it is as a kind of two-step construction. And the first step, we have a realizability model in a kind of fairly standard sense, which is a model where we have some kind of fancy version of Church's thesis. So Church's thesis says that all functions in the naturals to naturals are computable, and in this kind of fancier version, the function can be multi-valued and also it can be partial. And so if you go from functions to partial multi-functions, you might as well be talking about relations. So, but really, this is a kind of Church's thesis. And also that there's some kind of fancy, barely recognizable version of Markov's principles. Yeah. So I should have listed some names here. So this is coming from a paper by Hoffman, Streiter, and Van Osten, I think, if I remember correctly. So they show that there's this kind of very fancy version of Markov's principles, which is useful for things. Okay. And then inside that realizability, inside that realizability model, we construct another model, which is a reflective subuniverse. So this is using the kind of general theory of reflective subuniverse and modalities, following Wakelin, Swan, and Spitters. So I won't be defining that today, so I hope everyone's familiar with it to some amount. Okay. So how do we define these reflective subuniverses? I mean, what is a concrete description of them? So the concrete description is based on a formulation of the axiom LLPO, and in fact a variant of LLPO with LLPO n, with each number n. And we state this using NAT infinity, n infinity. So this is a set of decreasing binary sequences, which is a lattice with the lattice structure defined pointwise. And so the way we visualize this is that we have a sequence which starts off at 1, and maybe it's 1 forever. But if we kind of keep seeing 1s, we never know if it's going to drop down at 0 as soon as we stop looking. But once it has dropped down to 0, then it's fixed, then it's not going to go back up again. So that's how we kind of visualize these guys. And and then the top element is a sequence which just stays at 1 forever. Okay. So if it's not 1, then using Markov's principle, we will eventually find out, because we can just keep testing the sequence until we see where it hits 0. Then says LLPO says that if we have or LLPO n says that if you have n elements and the pairwise join is top, then one of the elements is equal to top. So in classical logic, so if we assume LPO, then we know that n minus 1 out of these n binary sequences are going to be equal to top, because LPO says that if the join of these two sequences is top, then at least one of them has to be to top. So that's it. So the question? So the lattice structure on 0, 1, where 1 is top and 0 is bottom, and then it's pointwise. Yeah, okay, and then we nullify. So this is the Wakelin Swan stuff that I hope people know to some extent. So we have a subuniverse where we force these propositions that there is at least 1 which is equal to top to be true. Okay, and then the corresponding subuniverse that we got is by construction exactly the type of all null types. So type is null for these propositions. If for every map one of these propositions to the type, there's a unique lift to 1 here. A unique pair consistent of this diagonal map and proof that the triangle meets. Okay, so yeah, so as I said, this is like one of my favorite kinds of realizability, and so I wanted to show some examples of proofs in district realizability to kind of illustrate why I like it. So I picked these two. Every generator of the nth one is modal with respect to the n plus 1. So the idea is you have a map from this proposition to this proposition. So this is a disjunction of n plus 1 things. This is a disjunction of n things. And then by computable choice, you can make this into a map from a finite set with n+1 elements to a finite set of n elements. By the pigeonhole principle, you have to have two things mapped to the same thing, and then we can kind of quite start. Okay. And then another lemma is that each modality is non-trivial. So to show that modality is non-trivial, well, we use computable choice again. So just tertiary thesis this time, and kind of by assumption we can so by assumption we have at least one of the n clauses in the disjunction is true. And then we can choose one by computable choice, and then we can do this also in a computable way. And then we can diagonalize once we've done this in a computable way. So I like this because we have this some kind of combinatorial almost argument using pigeonhole principle, and then we have a diagonal argument, which is definitely commutability theory, and these are both coming up in literature vice okay, so yeah, so we can use that to show that well, so the two lemmas that I showed, we can use them to show that the inclusion from each universe to the next does not preserve propositional truncation. And then we can also show that these universes, these sub-universes, are closed under co-products and W types. I think that they also contain the circle type, but this is using some kind of fancy new model of type theory due to Christian Zappler. So still, so checking that we can actually apply this model and kind of combine it with all the other stuff is work in progress, if you like, but it's probably fine. Okay. So yeah, and then so one construction of just to get a non-regular locally Cartesian closed category is very simple. We just take the union of all of these sub-universes, and then in each sub-universe there's a type where the truncation doesn't exist until you go up to the next sub-universe. So if we just take the union over all of them, then there's no universe which contains all of the truncations. So yeah, okay. But this is a bit limited if we want to define universes, because, well, okay, one way of defining universes that we might try, we don't get sigma types, and another way, we have this kind of issue that I mentioned at the beginning, where it does satisfy like a weak version of truncation, where we only have the elimination principle restricted to each universe. So for each Ln, we do have like a kind of a local truncation, where the elimination principle is restricted to types at that universe level end. So we can fix that using gluing, and in particular, using the this version of gluing due to well, presentation of gluing, if you like, due to Murray Schulman, which is using category theory, which I like, and it's for homotopy type theory, which I need for these results here. So given a model of type theory, E, the arrow category E is also a model of fundamental type theory, and in particular we can describe the universes explicitly. So this is how the universe, so given a pair of universes U and V, we can construct a new universe in the arrow category like this. Okay. We don't do that because that's like a nice, good, well-behaved universe, which does have propositional truncation if the original model does. So instead we do like a weird, kind of slightly funny universe, which you wouldn't usually like because it doesn't have nice properties like being closed under propositional truncation in general. So we just take the inclusion from, so given an inclusion from one universe to the other, we just view this as an object in the arrow category, And yeah, and in fact, we can view it as a universe, if you like. And using the Lifshitz realizability stuff from the previous slides, we can get examples where the inclusion of universes preserves a bunch of types constructors, including, containing the circle type, preserving W types, preserving disjoint sums, empty type as well, let's say. Then the resulting universe in Yarrow category has all of that stuff, but the inclusion does not preserve propositional truncation. And then you can show that the universe as an object in Yarrow category does not preserve propositional truncation, even this kind of weaker local version where we restrict the elimination principle to the universe. And then just a bit of a trick, combine this with the other trick if you like, we can get a cumulative sequence of universes, infinite cumulative sequence of universes this way, which are all univalent. If you like univalent, or if you like extensional type theory, then they're just universes. So that's more or less it. So I'd like to have a kind of more direct interpretation of S1 if possible, which doesn't need to use this kind of fancy new stuff like Christian. Nice to have other high inductive types as well. I think a bunch of Eilenberg plane spaces should probably work. And this is actually kind of quite a general technique, so maybe there's other applications as well, the kind of general technique.